Welcome back to Mythbusters. Now you might notice that a few things are different around here.
Due to recent cutback, the show's quality will not be the same.
We lost a lot of our supporters due to our last episode, how many domestic cats does it take to take down a full-grown man?
Rest in peace, Grant.
Well, what myth are we busting today, Jamie?
Today's myth is from the show Stranger Things.
Great, which scene?
The scene is where 11 flipped the van with her mind. So, we need to determine how much force the little girl needs to exert to lift the van and how much power it took to do it.
So we're gonna need to know the height of the van.
Exactly. From this shot, here we can use the height of the middle of the van from the ground as our distance.
And how do we do that?
Well, I did some researching and found that the actor on the far left is about 153 centimeters tall.
But he's on a bike, so his height will be off.
Easy solution. We need to find his foot size.
Buddy, let me get this straight. You're at home looking up child actors and their foot sizes?
No. It's not like that. When a bike properly fits you, your toes should just be able to reach the ground.
Checks out.
The average height to foot ratio is 6.6 to 1. Therefore, his foot size is about 23 centimeters, making his height on the bike about 176 centimeters.
I've got it. We need to use that shot and find the height of the van given the actor's height, so the van is about 3.5 actors above the ground. So therefore, we need to take 176 centimeters, his height on the bike, multiply it by 3.5, giving us 616 centimeters above the ground.
You got it, kiddo.
But now we need to know the mass of the van. According to USA Today, a van is about 2,460 kilograms plus the weight of the driver, which is about 75 kilograms, making it all 2,535 kilograms. Let's get to the drawing board.
Not quite yet. First, we need to know how long the force was applied for. Watching the footage over and over again leads me to the conclusion that it was applied for approximately 0.2 seconds. Now to the drawing board.
Let's go! First we begin by writing down our knowns. So I named the phase in which the force is applied the explosion phase. So the E phase, we know that the time is 0.2 seconds. The initial velocity is 0. We do not know the acceleration, we do not know the distance, and we do not know the final velocity. For the P phase, or the projectile phase, we know that the initial velocity equals the final velocity from the explosion phase. The final velocity is 0 meters per second. Acceleration due to gravity is negative 9.8 meters per second squared. And the distance we know to be the total distance minus the distance from the explosion phase. And we also know that the distance from the explosion phase plus the distance from the projectile phase equals 6.16 meters. We can then use the equation d equals initial velocity times time plus 1/2 at squared, sub in the values for the explosion phase, and work that through and get that the distance of the explosion phase is 0.1 times the final velocity. We can then sub in the values for the projectile phase into the equation v final squared equals v initial squared plus 2ad, work that through and get the distance for the projectile phase equals v initial squared over 19.62. And we know that the initial velocity of the projectile phase equals the final velocity of the explosion phase, and we know that the two distances added together equals the total distance of 6.16 meters. Therefore, we can take that equation, sub in what we just found from our first two, and get that the variable velocity is 10.056 meters per second. I then went back to our knowns. So for the explosion phase, we still have 0.2 seconds Initial velocity is 0. Acceleration, we still don't know. Distance, we still don't know. Final velocity, we just found out to be 10.056 meters per second. Over to the projectile phase, we now know that the initial velocity, because it's the same as the final velocity from the explosion phase, is 10.056 meters per second. And the final velocity continues to be 0 meters per second. Distance is the total distance minus the distance from the explosion phase, and acceleration due to gravity is still negative 9.8 meters per second squared. Next, we can use the equation final velocity squared equals initial velocity squared plus 2AD. Sub in the values for the projectile phase, and for the distance, we know that it's a total distance minus the distance to the explosion phase. Therefore, we find the distance for the explosion phase to be 1.0056 meters, and we know that added together they have to equal 6.16. Therefore, the distance for the projectile phase is 5.154 meters. I then went back to our knowns. For the explosion phase, we continue to have 0.2 seconds. Initial velocity 0. We still don't know acceleration, but we now know the distance is 1.0056 meters. Final velocity 10.056 meters per second. Projectile phase, initial velocity 10.056 meters per second. Final velocity 0 meters per second. Distance 5.154 meters. Acceleration due to gravity negative 9.81. We can then use the equation acceleration equals final velocity minus initial velocity over time. Work that through and find the acceleration of the explosion phase is 50.28 meters per second squared. Now we can go and get our F-net. Oh, I forgot to draw a free body diagram. There it is. Alright, so now we know F-net equals the force applied minus the force of gravity. Oh, and I forgot to define positive x. So positive x is up. So we know mass times acceleration equals force applied minus mass and acceleration due to gravity. We fill that in with our knowns and find that our force applied is 152,328.15 newtons. Next, we need to figure out the energy. So energy equals force times distance, and when we plug those numbers in, we get 153,181.18 joules. And then from there, we need to figure out the power. Power equals energy divided by time. We plug those numbers in. We get 765,905.9 watts. Converted to horsepower is 1,027.0965 horsepower, which is the equivalent to 6.5 Honda Civics DX model.
All right, Jamie, I think we can do this.
Let's give it a shot.
Jamie, I don't get it. I don't understand. Why can't I do this? What makes me and the 12-year-old girl different?
Well, she was under pressure to save her life, and I suppose the adrenaline was coursing through her body.
You know what we gotta do next.